How does freezing work in thermodynamics? Imagine a liquid cooling down and transforming into a solid, like water turning into ice. Have you ever wondered what actually happens during that change? Well, in thermodynamics, freezing is a fascinating process that involves more than just temperature dropping. It's about how heat energy is removed from a substance, causing its molecules to slow down and settle into a structured pattern. When a liquid cools, its molecules move faster when warm and slow down as it gets colder. Temperature measures the average energy of these molecules. As the temperature drops to the freezing point, the molecules lose enough energy that they start to stick together and form a solid. For water, this freezing point is 0 degrees Celsius or 32 degrees Fahrenheit. At this temperature, both liquid water and ice can exist side by side, which is called a phase equilibrium. During this phase change, the temperature stays nearly constant. That's because the heat being taken out of the water isn't lowering its temperature further. Instead, it's used to change the water from a liquid to a solid. This energy is called latent heat of fusion. It's like a hidden cost paid to make the transition happen without changing the temperature. Freezing happens in two main steps. First is nucleation, where tiny clusters of molecules form initial solid seeds. These seeds need to reach a certain size to become stable. Once stable, crystal growth begins, with more molecules joining the solid structure and expanding the ice crystals. As this process continues, the entire liquid gradually turns into a solid. As the freezing process releases latent heat into the surroundings, it can slow down the process. The system stays near the freezing temperature until all the liquid becomes solid. After that, if heat continues to be removed, the temperature can drop further. An interesting fact about water is that it expands when it freezes. Ice's molecular structure takes up more space than liquid water, which can cause pressure in confined spaces like pipes. That's why freezing water in pipes can sometimes lead to cracks or bursts. The speed of freezing also matters. Rapid freezing creates many small ice crystals that are less damaging, especially in food preservation. Slow freezing forms larger crystals that can break cell walls, leading to texture loss. The volume of liquid and how quickly heat is removed influence how long the process takes. Larger amounts of liquid take more time to freeze because more heat must be extracted. In summary, freezing in thermodynamics is about removing heat from a liquid, causing molecules to slow down and organize into a crystal structure. This process involves latent heat releases and volume change, depending on the substance. Understanding how freezing works helps in many areas, from keeping food fresh to designing systems that control temperature and fluids.